ahead and let you kick it off, Bernie, and when we get to it, we'll get to it if the rest of the members join.
Yeah, I feel like I should start wearing a disguise so people don't start getting sick of my face. I don't know what that would look like, but all right, we're gonna go ahead and share my screen. All right, everybody see this okay? Uh-oh. Can folks see this?
No, sir.
Uh-oh. It said screen attempt sharing failed. Try it again. Ah, there we go. How's that? Better?
Got it.
All right, so this is a module on physical and chemical properties of hazardous materials. And this one isn't particularly long. We'll probably get through the slides in maybe under an hour, and then we've got an activity that goes through one of our most useful resources to protect workers from chemicals, the old pocket guide. Well, we'll get into it. A lot of brain power went into this. So I made sure that I was trained and contacted the best and brightest minds in the chemical business. So rest assured, this will be good. I don't want to hear reports of anybody blowing stuff up after this class. So save it for the 4th of July. All right, so after this course, you'll be able to define what a property is and to differentiate between a physical and chemical property. List and describe at least 6 physical and chemical properties of hazardous materials and explain why knowing this can help you keep safe. Define the following types of radiation, alpha, beta, gamma, and neutron, and state which has the greatest health impact. And then use the pocket guide to look some of this stuff up. So what I want to do is kind of, I've recognized a lot of faces. Some people and names are new to me still though. So I'd like to find out who we are today, why you're taking the class. And, I'm Bernie Missoula. I'm industrial hygienist, director of health and safety for the FTI. And I've been doing this for about 26 years. So this is actually, this will be fun for me. I mean, all the stuff that I teach is fun for me. I know it's crazy, but my undergraduate work is in environmental chemistry. So it's always nice to go back to these roots. But unfortunately, a lot of the reasons why we're concerned about what we do on a job site goes back to chemicals. And, painters and the allied trades being what they are, whether it's putting in floor coverings or wall coverings, we're talking about chemical issues, right? And we still have that safety stuff like, falls from heights, getting struck by, et cetera. But our membership in the IPAT uses a lot of chemicals. So with that said, who do we have here today? And, let me know where you're from. And also, if you teach any classes that you think chemicals may be a part of in some form or fashion, that'll be nice to know too. So who'd like to go first?
I can go. So my name is Nuno Portella. I'm the Health and Safety Coordinator for FTI of New Jersey, District Council 711. I'm basically taking this class today because I needed a break from shoveling. No, I'm just kidding.
That's fair enough.
Now, this is something that I figure the more knowledge we have, the better I can help the members with information in a lot of the classes that we do.
Uh-oh. All right, thanks, Nuno. And I recognize you're on a lot of the courses that we run, so I'm happy to see that. So hopefully some of this stuff will help get you to a little bit more comfortable level or higher plane of teaching. And again, I always say this, I'm very thankful that all of you want to do training as part of your work, because you're going to affect a lot of people's lives that you might not even know how it happens at the end, but really this stuff, it's meaningful. We've got a lot of research on how important training is to workers' health and safety. So it's a really big deal. So thank you all. All right, who we have next?
I'm Mike Moreschi from Boston, DC 35 Boston. Like Nuno, I got in late because I was shoveling. This is important to me because whether or not you're using the chemicals, they're around all the jobs. We're exposed in some way or another, and with more than 50,000 chemical injury related illnesses and things like that happening every year, we can't know enough.
Yeah, that's a good point, Mark. Mike, just because you might not be using it yourself at that moment, there might be somebody around you on the job site that is, and that is your work area, right? So just because you don't have it in your hands, you're opening up a cover, somebody else next to you might be doing that, and you very well could be exposed. So that's a great point. Okay, welcome. Who else we got?
Tim Yost, DC 35, Boston. Industrial painter by trade, instructor now too. I think that this chemical class is probably going to be helpful. I think it will play into the GHS HAZCOM material that we give already. And, you can never really get enough of this stuff. The research is valuable, especially when you're given the class.
Yep, very much so. Yeah, and this is surely going to help if you do HAZCOM classes, right? All that data that comes on a safety data sheet or a label, if we don't know what that stuff means, and not just what something means, but how is that going to affect you as a worker out in the field? That's really what we want to finally impart to people. Right? Welcome. Who else we got?
My name is Don Golchuk. I'm from District Council 36. Taper by trade, safety coordinator here. And I just think that this subject is always an interesting subject because of the amount of new chemicals and stuff that come out every day, month, week, whatever. It's just an unreal amount, and we need to keep our members, informed of what they need to do and how to protect themselves.
Excellent. Welcome. Welcome. And your taper, huh? I like to meet you someday. Any tapers out
Yes.
there that can help me? Because let me tell you, when I finish off drywall, it looks like a modern day art project.
Yeah.
I don't want to tell you how much I have to sand off a wall. It's embarrassing.
Right. Sand and mud.
You definitely practice an art form there. I'll tell you that. All right. Thank you and welcome. Who else we got?
Hi, everyone. Good morning. This is Janet from District Council 36, just like Don, drywall coordinator. And just following up on what Don said, we always need to keep up and update all the chemicals that we work with out in the field, even if we don't have, we don't directly work with chemicals, but there's always somebody around us that does, and especially us with the dust and silica dust and the mud fumes, and it's always important. So
Yep, absolutely. Well, welcome.
thank you.
Anybody else?
Dave Headley with District Council 30, glazing instructor. Just keeping my knowledge going on all the stuff out there to continue the OSHA training and glazing using all of our chemicals that we use. So that's it.
Welcome. And Dave, where is District Council 30? I see you got palm trees there. Is that wishful thinking or is that?
Yeah, that's wishful thinking. We're just south of Chicago.
Okay. All right. All right. Welcome. Who else we got?
Justin Ocean, AC6, full-time drywall finishing instructor and safety instructor here. Been teaching full-time for about four years now.
Welcome. All right, anybody
Hi,
else?
this is Kyle Robbins. I'm an assistant instructor at DC 36. Taper by trade, been taping for about 12 years now. And I just started with this DC 36 about a month ago.
Okay. As an instructor, or you moved there and you started working under DC 36?
I just started as an instructor.
Oh, great. Welcome. Welcome. We need new blood. It's important. Excellent. Thank you. Teaching's a lot of fun, man. A lot of good stuff. All right. Who else we got?
My name is David Arvayo out of DC 30 as well, same as David Headley. I drywall finishing by trade and painting. So I do that for our apprentices, journeyman and safety. So just taking this course to expand and be able to add it to the OSHA 30s, OSHA 500s, 502s, and 510s.
Great. All right. Anybody else? Okay. That's it. You guys might not be able to hear this, but I hear some great music to my ears. I hear the sound of shoveling, which means one of my kids is out there shoveling off some walkways. It's good stuff. All right. So look, if you teach, like GHS HASCOM, like you said, if you do respirator training, you do any of, maybe the apprenticeship training that talks about anything that you're going to use out in the field, it's probably a chemical. If you do HAZWOPER training, there's so much stuff where having a better understanding of these physical and chemical properties of hazardous materials is going to be useful. So with that said, let's buckle up. And again, the goal is not to make anybody a chemist, but there are certainly, what I'm going to show you here, we can understand this stuff very easily, and it's very applicable to protecting workers out on a site. We're going to give lots of examples of that as we're going through. So first off, hazardous materials, they've got observable and measurable properties that enable us to identify them, just like a car. So, here are some properties of a car. You got a make, model, year, and color, right? So pretty much everything out there in the world has properties to it that we can identify. Physical and chemical properties are two types that hazardous materials have that you can identify them with, evaluate them, figure out how they're going to behave out in the world. So we've got physical properties. These are things that you can observe without changing the substance into something else, as opposed to the chemical properties. These are characteristics that involved when a hazardous material interacts with another chemical, and it actually changes its chemical makeup. So it becomes something different after its interaction. So for physical properties, we've got some examples of hardness, melting point, color, texture, density. So we can see all these things out in the world, and it's not actually changing that chemical. If we look at, the density of lead, it's always going to be lead. Now, chemical properties, on the other hand, are some examples of, we got flammability, reactivity, ionization potential. So if it's bombarded with some kind of an energy that's going to make it give off its electrons and, maybe change it into a different chemical form, heat of combustion, and toxicity. So these are things where we look at these properties, and if it's occurring, they're actually going to change. That's one of the tricky things about fires. And one of the reasons why firefighters have such an incredible incidence of cancers, because really, what are they doing? They're going to an uncontrolled chemistry experiment, right? They're going into a building, and think about all the building materials. Think about all the building materials that you use in the IUPAT trades, right? From flooring to drywall, different paints. Imagine lighting all that on fire, and what is going to be created with that experiment. We don't know. We've got classes of chemicals, but there's so much reactivity going on during a fire. It's crazy. And unfortunately, some firefighters don't wear their SCBAs correctly. And then after a fire, when they do what we call overhaul, which is where they go in, they poke around, make sure the fire is out, and they look for clues as to what might have happened. Research through NIOSH has found that many firefighters don't wear their SCBAs or respirators during overhaul, which is unfortunate because they're becoming exposed to this stuff. So these are the two differences, physical and chemical properties. Chemicals are found in one of four phases or states: solid, liquid, gas, and plasma. And we're not really going to talk much about plasma here, because this is more something that deals with labs and research and things like that. The stuff that is tangible to us, that affects our everyday living, as solids, liquids, and gases. Now, each of these states can have a different type or subcategory. And that's applicable to workers for very important reasons. So let's give some examples. What are some subcategories of solids? And the folks who do the taping and the drywall finishing should be able to give me an example of this one. So we could have dusts, right, when we do all that sanding. What is asbestos turn into once it gets up into the air?
Deadly.
Deadly, yeah, deadly. Fibers, right? So we can have dust, we can have fibers. How about liquids? What are some other categories of liquids that you might be able to have? Think of what happens when you use a pressure washer. Things like mists.
Vapors.
Vapors. So we're going to throw that one down in the gas category. But vapors come from liquids and they're connected to how gases behave, and we're going to get into that. So for solids, we have aerosols, dust, fibers, and fumes. And it's important that we understand this language. Usually I'm not a big stickler for memorization, but some stuff we do want to make sure that sticks in our minds, because we're going to apply it over and over again out in the field. And the more that you use this stuff, the easier it becomes to remember. So an aerosol is a finely divided solid or even a liquid that's suspended in a fluid medium. In this case, it's air, but you can have an aerosol in a liquid. Then there's dust, which is, tiny particles, and a dust is an aerosol. A fiber is an aerosol if it's suspended in air. A fume, what is a fume? What's a work process that's typically associated with producing fumes?
Burning.
What's that?
Burning.
It could be burning if it's something like high torch cutting on a metal. Do we have any certified welders here today? Yeah. So welding fume, that's a big one. So what a fume is you're superheating metal up. At such a high temperature, it actually becomes a vapor and it vaporizes. But as soon as it gets up from that surface of where that heat is, it condenses really quickly back into a solid. But it's a very unique solid. They're very, very small, almost perfectly spherical particles of that metal. And that's what makes them very dangerous, because with their shape and how tiny they are, they're able to reach our deep lung pretty easily. So fumes are particularly nasty. And oftentimes you'll probably hear, like, if people are talking on the news or something, you got a reporter and they say, oh, the fumes here at the gas station are overwhelming. Well, those aren't fumes. Those are gases and vapors that are coming off of that liquid gasoline. And that's important because when we're doing things like selecting respirators, we need to know this stuff. How about liquid? So again, we can have an aerosol liquid, although it's not typically something that we care about for worker health and safety. You can have mists, like if you're doing any kind of pressure washing, stuff like that, where you create overspray. You can also have mists of painting, right? So if you're using any kind of paint spray operation, you're going to be creating a mist. We can also have gels and adhesives are other examples of liquids. And then gases are just a bunch of different atoms that come in pairs. So a chlorine atom can be a gas if you have chlorine times 2. So Cl2 would be chlorine gas. We've got acetylene, oxygen, carbon monoxide. There's a bunch of gases out there.
Hey, Bernie.
Yeah.
Just a little side note. I mean, even with the paints, when you're spray painting, there's materials out there that you could generate both a mist and a dust.
Yeah.
You could use like a dry fall, for example, which comes out in a mist, but once it atomizes and it dries, the overspray comes down in the dust.
Okay, so thank you, Noodle. So this is great stuff for me to know. So one of my short-term goals over the next year is to learn as much about the IPAT trades as I can, because if I don't do that, I'm not going to be able to apply what I know and transfer what I know to folks to help all of you out in the field. So thanks. That's important stuff for me to know. Okay, that's interesting. Yeah. So, and again, let's take respirator selection, right? You know that you cannot select an N95 to protect you against what? Gases, right? And vice versa. So we need to make sure that we understand what kind of form the chemicals are in, so we can take the right precautions, whether it be implementing engineering controls or if we're selecting something like a respirator. So each one of these phases of matter actually have some unique properties that are pretty interesting as well. And we're going to talk about how this relates to worker health and safety. So gases, they've got an undefined size, shape, or coverage area. So let's say if I had a container of a gasoline and I brought it into, one of your training centers, one of your classrooms, and I opened it up, that gas is going to spread out equally through that whole room, and it's going to become the shape of that room. So if you've got slanted ceilings or things like that, it's going to fill that shape and it's going to look like that. And even though you can't see it, those gas molecules are bouncing off the walls very uniformly. And that's a good thing, because if those things ever collected in one spot, that would be bad, because if that happened with oxygen, we could walk into a room where there's a pool of oxygen in a corner, but nothing where we are, we're going to pass out. So thankfully, gases behave according to the laws of physics, and they will fill the shape of that room and disperse equally. Now, how does this affect worker protection? Well, let's say if you're using a gas for a product, maybe it's a welding, or maybe it's a propellant from a can or something like that. Do you think the concentration might be different between a small room and a big room as you're letting that gas out? And I'll ask it to you in a different way. Let's say I had this is not a seltzer can. Come with me on a journey of imagination for a moment. Let's pretend that this is a can of chlorine gas. And I bring it into this room that I'm in here. It's about, 12 by 12, 8-foot ceiling, and I release it. It's going to fill this room. It's going to have some concentration based on how much chlorine gas is in here and the size of my room. What if I brought the same container then into a sports stadium, maybe an indoor basketball arena, and I open that up? Same thing's going to happen. At some point, it's going to fill the whole entire space, equally distributed. Which one of those is going to have a higher concentration of chlorine gas?
Smaller room.
Yeah, the smaller room. So, if you've got a worker who's doing the same process with something that can create either a gas or even a vapor, and they switch from, the volume of space that they're in, they could be putting themselves in either more harm or less harm. So these are important concepts to understand. Good work. Liquids, they have a fixed volume, right? So this can is it's a fixed volume here. So however many, this is a 12-ounce can, but the shape and the surface area might change depending upon its container. So I can pour this out on the floor, which I'm not going to do because I want to drink it. And it's going to take the shape of spreading out. I could pour it into a different container. It's going to take that shape of the container. The surface area might change. For instance, if I'm pouring it on the floor, now it's going to create and cover bigger surface area. However, the volume stays fixed. So however many, ounces of liquid are in this can, it stays that way. Not so with a gas. Then we've got solids. So these have a fixed size, shape, and a surface area. So like, my desk, this Sharpie, solid, it's not going to change. It looks this way. Fixed size, fixed shape, and a fixed surface area, not going to change. However, what could happen to solids during our everyday work environment? You can manipulate them, right? You can sand them, you can break them up, you can drill them, create friction. That's going to create something that's going to break that solid down potentially, and then it can become dispersed up into the air and create an aerosol or what have you. Now, matter can change phases. It's based on the different physical properties that it has, and we're going to cover some of those during this class. So solids can go to a gas form. We call it sublimation if you go from a solid to a gas, or a gas can be created into a solid through deposition. Solids can go from liquids and vice versa, freezing and melting, and liquids can go from gas and vice versa from condensation or vaporization. So if you've got a liquid that's turning into a vapor, and we'll forget the plasma for now. So all these things are connected. So here's some common properties of chemicals that we're going to go through, because these things are really important for worker protection. We got melting point, pH, vapor, and gas density. vapor pressure, boiling point, flash point, and flammable limits. All these things very important for protecting workers. First, we've got melting and freezing point. So it's the temperature at which a material is going to change from a solid to a liquid or back, right? How could this affect us, our health and safety as a worker? Let's say if you're climbing around on some scaffolding and, you know, it's a little rainy out and it's 40 degrees, but you show up to work the next day and now it's 29 degrees.
Can make things slick.
Yeah. So here's an example of melting and freezing point being, you know, pretty important for that person walking up on the scaffolding. Vapor pressure is a measure of a liquid's ability to evaporate or give off vapors, and those and how they're going to spread. So, you know, here's an example. We've got a closed system, and in most of our work, we're not going to be in a closed system unless. Can you think of any environments where you might be as a worker that's somewhat of a closed system?
Confined space, tanks.
Yeah, yes, confined space or a tank, absolutely, good. Oh, no, go back. So this is a somewhat closed system. So this liquid here is going to vaporize. So what's going to happen is molecules of that liquid are going to escape the liquid form and get into what we call a gaseous form. So a vapor is going to behave for the most part like a gas. It's not a gas, but it's going to behave like one. At some point, you're going to have so much vapor in this, what we call headspace above the liquid. And in here, it's confined because we put a cork in this, this flask, that it becomes at an equilibrium. So there's so much vapor that's getting out, and at the same time, it's going to be trying to sneak back into liquid. At some point, it's going to become equilibrated. So it's not going to be able to get into the gaseous phase anymore. And so it finds a balance. Now, imagine if you had a closed system, and now vapor pressure is dependent on what? Vapor pressure is intimately connected with something.
Temperature.
Temperature, right. What do you think would happen if you have a closed system and you start heating it up?
Explosion.
Yeah, explosion. If the integrity of this container fails, that's it. And we've got some really devastating examples of how vapor pressure exceeded a container's ability to hold it under heat. So it builds up pressure. And we're going to be able to find the vapor pressure in most chemicals that we work with. The Pocket Guide is a great resource. You know, when you look on probably a can of a lot of the materials that you might use out in the field, it's going to list its materials. You can see it on the SDS, and you'll be able to find and determine the vapor pressure. They can be very wide ranging. So here's an example of propane. Its vapor pressure is 6,384 millimeters of mercury, as opposed to something that you might use out in the field, toluene, 21 millimeters of mercury. And 760 millimeters of mercury is what we consider atmospheric pressure. So if I walked outside my door right now, typically that's going to be 1 atmosphere or 760 millimeters of mercury. That's what we call atmospheric pressure. It's going to change if I decide to hike up Everest, right? But for the most part, it's 760. And that also equals 14.7 PSI and 407 inches of water. So you might see these presented differently, but they all mean the same. Each one of these equals each other. In the Pocket Guide, you might see things differently where you're looking at liquefied or compressed gases. For instance, if I look up propane here in my Pocket Guide, I can see that its vapor pressure is listed as 8.4 atmospheres. And the reason why is if I divided 760 into this, I would get 8.4 atmospheres. They don't want to list a huge number in the Pocket Guide. So if you're dealing with liquefied or compressed gases, they're going to have it in the pocket guide in atmospheres instead, and you'd have to convert it. But for smaller stuff, you'll see millimeters of mercury. And again, these are things that we use, you know, in the painting world. How many people here have used toluene or xylene? Right? And a rule of thumb that we use in industrial hygiene is if we say a chemical has a vapor pressure of 10 millimeters of mercury or more, it is volatile enough to be a concern for worker safety. It doesn't mean that it's not toxic or something like that. If it's got, you know, a vapor pressure of 2, that's not what we're saying. We're saying that if it's got a vapor pressure of 10 or more, it's going to get up into the air easily enough where you need to be concerned about that being airborne. And again, toluene, it's one of the few chemicals where we actually have a threshold limit value for exposure through your skin, because if it gets up into the air, and that happens to be 50 parts per million, the ACGIH has designated a skin exposure limit for toluene at 50 ppm. That means that if there's 50 ppm of toluene vapor in the air, you have to be concerned about protecting your skin through contact with it, because it's fat soluble. It's going to enter your body through your skin. So even if you had a respirator on, you know, the ACGIH is saying that's not enough to protect yourself. Boiling point, of a substance is the temperature at which the vapor pressure of the liquid equals the environmental pressure surrounding the liquid. So in other words, you know, the boiling point, if I start to heat this can of seltzer up, it's going to be in comparison to the vapor pressure around the outdoors here in the air. How many people here have boiled water? All right, how can you get water to boil faster without increasing the heat?
Put salt in it.
No. Salt will actually make it change the boiling temperature or reduce it, because you're putting an impurity into the water. We're not going to get into that in this class, but one of the ways that we can look at how pure a chemical is looking at its melting point and boiling point. If those things are off, it's usually because there's an impurity.
Put a lid on the pot.
Yeah, put a lid on the pot. Very good. How come? What did you change?
You're building pressure.
Yeah, you cut off that water in the pot from the environment around it, right? By putting that lid on. So all of a sudden you've created a different environmental factor there, which is the headspace above that liquid. And so you're going to make it boil faster. Water boils really quick when it's way up top. If you're on top of Mount Everest, you're going to boil water at a much lower temperature because there's not as much vapor pressure around. All right, persistence refers to how long the material remains upon release. So you probably heard, you know, if you've taken the PCB class that we did either a couple weeks ago or back in the summer, we talked about the persistence of PCBs. What does that mean? What does it mean for something to persist?
How it stays around.
Yeah, it stays around. So the problem is a lot of pesticides are very persistent, because if you're going to, you know, spend all that money on a pesticide and then deliver it out to a crop or something like that, or spray it around your house to kill those nasty looking spiders. Yes, Bernard's afraid of spiders. Don't like them. You want to see me jump, throw a spider out there. You don't want it to evaporate. You want it to stick around. So think of it like glue, right? Glue is pretty damn persistent. But unfortunately, that can create a different issue for our health, right? As a worker, or as you know, somebody in the general public, depending upon what chemical we're talking about. So basically, persistent materials don't evaporate within 24 hours, and you know, non-persistent ones will evaporate within that 24-hour period. And this one here is going to be a little bit harder to determine from, it's not really going to be listed on an SDS sheet or a chemical label, something like that. You're going to have to look up this chemical to do a little research. So if you're ever dealing with something you're not familiar with, you might have to do a little bit more extra digging. Now, as far as like, you know, an IPA team member that's on a job site, how would persistence of a chemical maybe affect my health?
No, if it's no longer in use and you're not wearing the PPE for when it's being applied, and you think you're safe, you don't know you may just enter that area after that process had been taking place and it's still there.
Right.
You get the exposure.
Right. Yeah. And I mean, that could even be, that could even cross different trades and stuff and timeframes. So, I mean, you could have somebody in there doing who knows what with their chemical, a day or 2 days before. If it's very persistent, you find yourself in there, you might not have any idea what happened. And then all of a sudden you're getting a reaction. So this kind of thing can be tricky. That's why it's really important, especially for large jobs, that general contractor have one qualified health and safety person, to be managing this kind of stuff. It's important. We want to make sure that one task of work is not going to negatively affect another task of work. Good. Sublimation is the ability for material to change from a solid right into a gas without becoming a liquid. So the best example here is what I've got in front of us. Anybody know what this is?
Liquid nitrogen.
Nope. So liquid nitrogen is a liquid. So that's, if you let that out in the environment, it would go right to a gaseous form.
Dry ice.
Dry ice. Yep, that's right. Yep. It's dry ice is frozen carbon dioxide, and it's negative 74, I think, is its freezing point, which is really damn cold. And in fact, some of our COVID-19 vaccines require storage temperatures colder than dry ice. So they're like what? One's I think negative 104, one's negative 90 something. So that's cold. I don't know if anybody has had the unfortunate experience of touching dry ice with your finger. What happens? Burns, right? It's so cold, instant frostbite of those skin cells. Volatile chemicals readily evaporate at 70 degrees Fahrenheit and atmospheric pressure. They typically have low boiling points, so you don't have to add a lot of heat to make that boil. And then they've usually got, high vapor pressures. So those things are really volatile. So it's important if you're gonna, be doing work with these kinds of chemicals that you take the right precautions. If you've got something that's really volatile, what kinds of work conditions do you think you'd like to have set up, or work controls if someone's using a highly volatile chemical?
Ventilation.
Yeah, absolutely. Ventilation. Good. And if that's not sufficient, then you got to go to the right kind of PPE, right? The right kind of respirator, and potentially skin protection. And it's also important too, as we're going to get into the next phase, is it's the next couple of slides. What actually burns? So what's the actual thing that's on fire when you see a fire?
Vapors burn.
Yeah, it's the vapors burn. So like, if I light this book on fire, it's not the paper that's burning. What's happening is this is getting hot, and it's heating up so much that the paper, the cardboard, the ink, it's starting to release vapors. And if there's enough heat around, those vapors are going to burn. That's why we have the phenomena of a flashover. Anybody know what a flashover is? Let's say you got your room heating up, and it's everything, my chair, the paint on my walls, the picture frames, books, whatever. It's heating up enough where all those things start to give off vapors. And at some point, if you've got enough of an ignition source in there, the whole room just goes poof, and you see this giant giant flame roll over the whole room. That's the vapor effect of flashover. It's not a good thing to be as a firefighter if you're in that room. So everything is heated up to the point where it's providing fuel. And so that's important. If you are in a confined space, what are you using as a worker that might be potentially vaporizing and providing fuel? Anybody recognize this? A long time ago, we used to call it the fire triangle, but now we call it the fire tetrahedron. So, these 4 things have to be present for a fire. You've got to have oxygen or a fuel source. You can also have something that's an oxidizer. like pool chemicals, you'll see that oxidizer yellow symbol on. Heat or an ignition source, and fuel. But the fourth thing that NFPA added, I don't know if it was late 90s or early 2000s, was a chain reaction, because I can prevent the fire from continuing by taking away one of these three elements here, right? So if I've got, oh, I don't know, a structure fire and I throw water on it, what does it do? Which one of these elements does water take away?
Heat.
Heat, yeah. Water is the world's greatest heat sink. It's great. How about if I had a, I don't know, let's say a toluene fire, and I throw foam on it? What does the foam take away?
Oxygen.
That's right, you smother it, you take oxygen away. And fuel, this is a little bit harder. You either have to let it burn itself out, or you can do pre-burning to try to prevent a fire from going further, which is what you might see them do if they're doing wildland firefighting. And then by doing that, you're breaking that chain reaction, right? So as I mentioned before, if you've got a fire, it's an uncontrolled experiment, which makes it very deadly, right? So you don't know what kind of chemicals you could be walking into. So the flash point, very important thing. It's the minimum temperature at which a liquid gives off vapor in sufficient concentration to form an ignitable mixture above that surface. So, whatever chemical this is, chemical X is going to have some flash point. That's the ambient temperature, what's around it, where it's going to give off enough vapors for fuel to be sufficiently lit on fire if you had ignition. And that's real important. Gasoline's flash point is incredibly low. Let's see.
Negative 45 degrees.
Thank you. So where could I be not worried about dumping out 5 gallons of gasoline and starting a fire? Certainly not in Arizona. Not right now in New England. Maybe in Greenland or something. So you're going to have to find some ambient temperature that's colder than, what'd you say, Nuno? 45, negative 45?
Correct.
I don't know. Siberia in the winter. So gasoline is such a problem for firefighters when there's gasoline spills, because they have to be worried about that as a flame hazard, no matter what temperature they're in. And this can change. So there could be a difference. Let's take toluene. What's somebody look up toluene's flash point. For the people who have a hard copy NIOSH pocket guide, you rock.
Just a Google search shows it's 40 degrees.
Okay, so 40 degrees Fahrenheit. So that could be, a different hazard if I was working with toluene when it was 30 degrees out, right, in New York, or 90 degrees out in Las Vegas, right? So it's important to understand this, because fire is a very real hazard depending upon what you're doing for work. Good. Now we come to the flammable limit. So we've got a lower explosive limit, which is the minimum concentration of vapor or fuel in air that you need to have for a fire. And then the upper explosive limit is the maximum amount that you need to have in air for a fire. And then the flammable range is that distance between the two. And we'll look at that here. This is where I love being in a real classroom, because I'll have a whiteboard or flip chart paper or something when I do a bunch of diagrams, but this is what I got. So if we look at the concentration of vapor and gas in air, just where we are, you're going to have from 0 to 100% of anything, right? And we can manipulate that by introducing something into this room. So at some point, let's say if I take my, let's stick with toluene. What's the lower explosive limit of toluene? And as you're looking that up, what I'm going to do is I'm going to take a can of toluene, I'm going to take the cap off and let it sit in the room.
1.1%.
1.4?
1.1.
1.1, okay. So as I took the cap off of that vat of toluene, what's going to happen over time? And let's say it is 40 degrees. So we're at its flash point. It's going to start evaporating into the room, right? At some point, I'm going to hit 1.1% of airborne concentration of toluene vapors in the air, which means what?
Flammable range.
Yeah, I'm in that flammable area. I've got enough fuel now. I have enough toluene where if I had an ignition source, I'm in trouble. It's going to light on fire. And then if I allow it to sit open, it's going to keep evaporating into the air because I have enough volume in there, and it's not going to reach equilibrium with atmospheric pressure. I'm going to hit the upper explosive limit. And for toluene, what is that?
7.1.
7.1, okay. So that means that 7.1% of toluene vapors in air. If I go above that, it's going to be too fuel rich. So if I did have ignition or heat, it's likely not going to flam up. Kind of the same thing that happens if you flood your carburetor. You got too much gasoline. You have an imbalance of fuel and oxygen mixture. So even with your spark, you can't get that thing to fire up, right? Now the problem is this. I don't know if I have it on the slide or not. No, I don't. So 1% of anything in air by volume is equal to 10,000 parts per million. Okay. So let's say if I was at the lower explosive limit of toluene, we said it was 1.1. So that would be 11,000 parts per million in air, right? So that's what my concentration is of toluene in air. Could somebody please tell me what the IDLH is, the immediately dangerous to life or health value is for toluene?
500 parts per million.
500 parts per million. Okay, so I don't know about you, but I think 500 parts per million as an IDLH is much lower than 11,000 parts per million, which is also the LEL, right? So you see now how LELs, flash points, vapor pressures, and toxicity values are also mixed up together. So before I'm worried about, toluene catching on fire, I might have my lungs melt down from toluene vapor. And it, might not necessarily work out that way in the real world, but these are all things that are interconnected, and we do have to think about it. The other thing is, we don't want to hedge our bets that if we're way up here in a flammable range, we're fine. And how would we be up here? Maybe we're in a level A hazmat suit and we're doing some kind of work to stop an emergency. There can be a lot of things that happen that could all of a sudden bring that fuel level right down into the flammable range. For instance, maybe somebody opens a bay door or a garage door, or they open up some kind of a hatch or something, and you've got mixing is going to happen very quickly. You can bring an area down into a flammable range, even if you're up in the fuel rich area, pretty quickly. And so if there was an ignition source, you could have a flashover. So, everything that's, in this book, if it's flammable, if it has a flammable range, they're typically a little different. So we see gasoline, right? It's got somewhat of a narrow range. And hydrous ammonia, even though it is considered flammable under the Department of Transportation. Natural gas got a pretty wide range. Anything over 12, I'm really concerned about. If you've got a flammable range that is so large, that means there's very little room for error. So look at acetylene, where you might use with acetylene torch. This flammable range is gigantic, right? 97.5% flammable range. Wow. Ethyl ether, again, pretty big, 34% flammable range. So it's important when you're looking, at the stuff that you got folks using, you want to look these things up. Look, you could be using some of these chemicals near a generator or something that's producing heat. an unfortunate example, and the folks that are at DC 35 might recall this back in the late 90s that happened. There was a Vietnamese population of workers, specifically, they did a lot of floor refinishing in the Boston area, and they were using methylene chloride as a kind of a solvent to throw down on the floor, and then they're trying to sand off and strip off the old coating on the floor. There were a number of fires that occurred, including some fatalities. They didn't have HAZCOM training. They didn't know about this. They just said, they thought, hey, this methylene chloride works good at helping me sand this stuff off. And so there was this issue, and NIOSH investigated it, and they found the root cause. And one of them was, methylene chloride has a flammable range, and the heat source were these floor sanders. Unfortunate. So just because you think, well, geez, the work I'm doing, it doesn't relate to something catching on fire, it very well may. That's why it's important to look at the work we're doing and marry that up to the chemicals and see what the possibilities are and prevent them. So let's do this little activity. What would make a chemical really flammable? So something that would give me, nightmares if somebody was using it. Would that be a lower or higher flash point? What would make it more flammable?
Lower.
That's right, lower.
Yeah.
The good example is gasoline. How about vapor pressure, lower or higher?
Higher.
Higher? Yep, good. Things that have vapor pressures that are, like I said, over 10, we need to worry about it. If you've got stuff that has vapor pressures over, or close to 100, those are really volatile. That stuff's going to evaporate very quickly. How about an LEL? Smaller range or larger range? What would make it more flammable?
Lower.
So a smaller range would be more concerning to you?
Larger range.
Right.
I thought you meant actual percentage.
What's that?
I thought you meant lower actual percentage.
Oh, I'm sorry. You know what? I was looking at my bottom. I meant LEL. So the lower explosive limit. Yeah. So the closer the LEL is to 0, the more flammable it is. I apologize. I was thinking flammable range, and then I just answered the question. So would a smaller or larger flammable range make it more flammable? Larger, right. I got more to worry about, right? That acetylene example, barely any of it has to get into the air to be flammable. And then it can keep getting into the air and it's still going to stay flammable. So you can just use this little guide, when you're looking at the properties of the chemicals that you're going to be using out in the field, and do a quick risk assessment. And from there you can say, all right, this is, concerning enough for flammability that we got to make sure we've got some controls in place. Any comments or questions about any of that stuff that we looked at so far? Just a couple more to go here.
Yeah, I got something.
Yeah.
I know when we teach confined spaces, we talk about vapor density a lot.
Yes.
Is that something you're going to talk about? Or?
That is coming up. That is coming up.
All right. I won't interrupt that.
Absolutely. That's a good one. Good for you on asking. Reactivity is the potential for material to release energy either by itself or once it comes in contact with another material. It can either cause a fire, it could cause an explosion, it could release toxic vapors or gases. It could do all three. A good example is sodium metal, raw sodium metal. It's usually stored under oil. Once you throw that in water, kaboom. There's this great video from World War II of the Department of Energy rolling barrels, 55-gallon drums of sodium metal off the back of a truck down a cliff into a lake, and just huge explosions. And there was actually a sodium metal explosion that happened in Newton, I think it was Newton, Massachusetts. There was a small metal recycling business where they recycled precious metals and other metals of value on a micro scale. So it wasn't a large place, but nonetheless, there was no NFPA fire diamond around to be seen by a firefighter. There was a fire in there. Typically firefighters put the wet stuff on the red stuff. So they went in and opened up the hoses and boom, big explosion, building collapsed, firefighter died. And, you know, it's very reactive material, is sodium metal. You might use some stuff. Again, I don't know our trades well enough yet, you know, to determine that, but do you have any examples of materials that you work with that are reactive? Anything come to mind?
Stain, thinner. You put stain and thinner rags in a bucket and it'll start off.
Yeah, you just reminded me of the good old days of my dad putting linseed oil rags in a metal bucket, right? You don't want to do that. Those are actually they're auto ignite. Good. Okay. Good.
So you sometimes used to tell the apprentices to soak a rag with MEK, have it in the back pocket to clean stuff. The problem is when they put it in the back pocket and it generates heat. So that was always
Wow.
a good lesson for them to learn.
That's interesting. That's interesting. Please tell me that was 50 years ago.
Wasn't around then, Bernie.
How about any acids or bases? Do we use any acids or bases at all in any of our trades? Those are reactive, you know, especially if you're going to combine them with something that's on the other end of the pH scale. Even water. I learned this in, you know, in undergrad chemistry. Do what you oughta, add acid to water. Why? You want to add acid to water in little drops. You do not want to add water to acid because it's going to sputter because there's just a huge production of energy there. But if you add acid to water, all that water can dissipate the reaction and spread its energy out, but not so if you did it the other way. So again, a safety data sheet should say this, but you don't want to rely on it. So it's always a good backup plan to just look up the chemicals that you're using, especially if you're not familiar with them. So as I mentioned, you know, pH corrosivity describes acidity or alkalinity. pH is less than 7, we say it's acidic, 7 is neutral, and greater than 7 is basic, alkaline, or caustic. And pH is an aqueous measure in water. Not to get too deep into it, but it's basically the percent of free hydrogen ions in solution. And the more you got, the more acidic it is. And one of the issues on our pH scale is that 1 unit change, so going like from 7 to 6, is actually a 10 times change in corrosive power, because this is a logarithmic scale. To be able to fit the numbers on this scale, to go from 0 to 14. And we can see some stuff we got on here. We got battery acid, lemon juice, vinegar, right? Salt and vinegar chips, I love them. I don't know if anybody has had the unfortunate incident of inhaling when you're eating a salt and vinegar chip, but it burns the lungs a little bit. This is an area where adult fish die, and we've got some other examples here of what we might find in everyday products on the pH scale. Specific gravity, so this is the density of a substance compared to that of water, which would be 1. So something that's less than 1, it's going to be lighter, will float on water. Something that's heavy, larger than 1, it's going to sink. And if it's 1 or just about, it's the same as water. So it'll be kind of buoyant. And here I just got a couple of different examples. What would you say this specific gravity of this material was? Do you think that is greater or less than 1?
Less.
Less, right. That's just a good old oil spill. And we're going to compare a lot of stuff to 1. The density of air is 1. The density the water is 1. Which, let's see, who asked the question about this? Yeah, okay. So here's vapor density. So we've got vapor density and also relative gas density. Now, the pocket guide, if we're dealing with gases, it's going to give you a relative gas density. But if you're dealing with a liquid, it will not give you a vapor density. You've got to calculate that. And I'll show you how to do that on the next slide. It's pretty easy. So it's basically the weight of that vapor or gas compared to air, which is 1. So less than 1, again, it's going to rise. If it's greater than 1, it's going to sink. Why would this be important to know?
If you're in a confined space, that way you know where the gases are going to accumulate.
Yep. Also, if you're doing work on a larger scale, something like toluene. Well, let's go to this next example here. So this is how you calculate vapor density. Again, you don't have to do it with a gas, something like chlorine or carbon dioxide. It'll give you that in the pocket guide. But for a liquid, you do. So if you want to look at what the vapor density of toluene is, you gotta calculate that. So what you do is you take the molecular weight of the chemical, the liquid, and you're going to divide into that the molecular weight of air, which for most intents and purposes, again, unless you're on top of Everest, is 29. I saw a couple documentaries on Everest. There's actually frozen bodies still up there? I mean, it's some creepy stuff. And people who climb it, they just climb past the frozen bodies, man. Anyway, sorry, I digress. So it's 29, our molecular weight of air. So let's say if we took our example of toluene. So toluene's molecular weight is 92.14 grams. We divide it by air, 29. Our vapor density of toluene is 3.18. And I can tell you, let's say if you had, you're doing some work and somebody was on the 3rd floor of a building and they were using toluene to dissolve something for whatever reason. Maybe, there was a surface that was dirty. They're trying to clean it up. They need an industrial solvent, something that's heavy duty. You will smell toluene on floors 2 and floors 1. The vapor density of 3 is heavy. It will sink through floors. And we know that, the building's not that tight, right? There's lots of air movement between third floor, 2nd floor, et cetera. Even if you're talking about like a LEED building, you're still going to have, pockets of air movement. So this could be pretty concerning. I mean, if you've got somebody above you using a liquid with a heavy vapor density, that's going to be concerning for you because you might be getting exposed, with somebody using something above you. Was that Joe? Does somebody have a question or comment? No? Okay. All right, so that covers vapor density. So again, you gotta do this calculation yourself because the book won't give it. Sometimes the safety data sheet will, but I wouldn't count on it. And as far as the confined space issue, things can be so heavy that if you're in a confined space, it could stratify real close to the floor, where in somebody's breathing zone, if they're doing some work on their feet, they're standing up, they might not have a problem, but they could drop a tool, bend down to pick it up, and be succumbed by the vapor down there. And that we have case studies of that happening. That's why it's very important, to have confined space entry training, to have a permit, for a required confined space, to have an attendant, to use ventilation in confined spaces. Solubility, you're probably very used to this phenomena, as a painter. It's the ability of a solid, liquid, or gaseous substance to dissolve in water. So things that are soluble, they're going to dissolve pretty well. And what I mean by dissolve is that there is space between water molecules. So H2O, there's space between those molecules. So that other chemical, it's able to fit in between that space. That's what we mean by dissolve. Not the same as mixing up a turbid solution. So like if you took a bunch of sand and threw that in water, that's not dissolving. That's just mixing. That's making a heterogeneous mixture, not dissolving. Salt, however, you can take salt and throw that in water and that will dissolve. It will fill the spaces between the water molecules. So here's
Hey, Bernie, I have a question about that.
Yes, sir, David.
How does liquid temperature play into it? Because if you throw in salt into cold water or warm water, it's going to be totally different.
Very good. So what is going to dissolve? What is going to increase the solubility in water? Hot water or cold water?
Hot.
Yes. So the hot, so you can get water to hold more salt or sugar if you heat it up. That's how we make that. You know, have you ever made that that rock candy with the kids, right? So you keep adding sugar to water. And
Isn't that illegal?
No. This is the okay kind of rock candy. So you keep adding sugar, and what we do is then we say we super concentrate that solid in the water. And then what we can do is we can move that to the freezer right away. And if we do it properly, that solid, the sugar won't saturate out. It won't flocculate out. If you bump it and stuff like that, you might start to have a problem. But if you can keep all that sugar concentrated in the water, then you take it out, you start to add a string to it, and it's going to condense, you know, it's going to solidify around the string. You keep dipping it in, you got, you know, rock candy. Want to throw a little blue food coloring in? There you go. Now you're really talking a party. So yeah, so temperature, unfortunately, with most of the stuff we talked about, with vapor pressure, boiling point, solubility, that can all affect those properties. So
And also with vapor density too, wouldn't you be concerned about the flammable liquids because of the explosion fire hazard, knowing how to control the hazard?
Yep. And in fact, you know, if you have warmer air, well, let me ask you this: what is more dense, warm air or cold air? And if you want a hint, think about hot air balloons. Right? What happens? You heat up that air in the hot air balloon, and the molecules might be this close together. They start to expand, right? So they become lighter. So that body of air within that hot air balloon becomes lighter. It becomes less dense. So all the other air around it that's not heated, what happens? It starts to float. Wow, that's cool stuff, right? So you can actually affect, you know, vapor density by having a hotter environment. So what if you're doing work in like, oh, I don't know, a steam tunnel or something like that? I mean, you've probably walked in some of those tunnels, right? In buildings where you got the steam pipes running. As soon as you walk in there, you're like, oh man, why did I wear a sweatshirt today? So you can actually affect this. So that's a great point. And it's something that you, as a health and safety person that's on a site, you got to be cognizant of. Then we got miscible versus immiscible. So the ability to mix in any quantity. And again, you know, we can affect this by temperature. Viscosity, you probably deal with this quite a bit, right? Is the resistance of a liquid to flow. Generally, the thicker the liquid is, the more viscous it is, and we can also affect this by temperature. So here I got a couple things. I've got water, that's less viscous than oil, and that's less viscous than honey, right? But I can change this by putting it in the microwave if I want. Any comments or questions so far? Next, we're just gonna touch on radiation. I've got a whole class. Actually, I developed a radiological worker 2 class that's meant for people who would contact and disturb radiological material. But from that, I'm actually going to be teaching a basics of radiation physics and health effects of that in the winter sometime. So this is going to be, you know, important if you work on a Department of Energy site, and I know we have IUPAT members that do. If you work in a shipyard, and I know we've got members that do, this kind of stuff would be important. Also, I don't know if our trades use, you know, lasers at all, or you know, structural integrity meters, things like that, but those have radiological sources in them as well. So radiation is a property that certain atoms that emit particles, electromagnetic wave energy, or both spontaneously. Basically, radiation is energy in motion. If you see, so this one here, this trifoil, the yellow with the yellow background with the black, this is the old symbol. They should not be using this one anymore. It should just be this triangle symbol down here, which, I don't know, to me, it's a lot more clear if I see this, what I should be doing. I don't know if you can agree with me, but here I've got this little dude that's getting the hell out of there. So This, if you didn't have education and training on it, you might not know what it is. So again, this red triangle, this is the new one. There's 4 types of ionizing radiation. So by ionizing, I mean this stuff has enough energy in it where it can ionize or strip off or move electrons from atoms. Not a good thing. Alpha radiation is the most harmful one. And then we've got beta, gamma, and neutron. We don't see neutron radiation that much. And typically when we see any, what we call an isotope, something that is radioactive and can give off radiation, you typically will have all 3 forms of radiation given off to different levels for the most part. Alpha, though, however, is the worst one for us. It causes the most biological internal damage. And unfortunately, many of us have to worry about alpha radiation out in the general public. Can anybody give me the example of why or where I would worry about alpha radiation? Especially if you live in New England or parts of New York and New Jersey, Pennsylvania. Anybody ever hear of radon? Right, I got radon in the basement. That's not something you want to have somebody tell you. So radon is a radioisotope that's a product of the decay chain of uranium. And so if you've got that in the ground, it happens to be in a lot of places that granite is found. So like in, Vermont, New York, New Hampshire, Massachusetts, Maine. And it behaves like a gas. And what's going to happen is if you've got, cracks and things like that in your basement, you can have alpha radiation in the form of radon seep into your house. And it is very damaging to your lungs. So much so that alpha radon, which is alpha radiation, is the 2nd leading cause of lung cancer in the country, right behind cigarette smoke. So it's very dangerous. So if you happen to live in an area that has a lot of alpha radiation through radon, you want to get that evaluated in your home and get it fixed. And I'll talk about that a lot during the health physics course. You can also have it affect your water. So if you have well water and you have sources of uranium around, you are going to get radon in your well water, and you want to be able to take care of that as well, because you don't want to drink it and you don't want to breathe that in when it gets released from you turning on your tap. So what specifically are some characteristics for alpha radiation? It's fairly large in mass, so it has a lot of weight to it. And it's got this +2 charge, which is what makes it very deadly. It strips off electrons from our cells. So that's not good. It damages our cells because of this +2 charge. It doesn't travel very far though, so that's the good news. Like if this pen was a source of alpha radiation and I put it on the desk, which you can't see in front of me, I'm not going to get affected by it right now, unless it happens to float up on the currents and things like that. That's why the radon is dangerous for us, because it's going to float and move in air. It deposits a large amount of energy in a short travel distance. So even though it only travels about 2 inches, it disperses a lot of energy, which is damaging to our tissues. And it's an eternal hazard. The good news is, don't say I don't use high-tech props. Alpha radiation can be stopped by a sheet of paper. So if that pen was alpha radiation and I put paper over it, it stops it. Intact skin, same thing. So we can be protected from it fairly easily as long as it does not get into our lungs. To shield it, again, intact skin, piece of plastic or paper, something lightweight. And when I teach this stuff in the classroom, I do actually have some pretty fun activities to do. So I've got different radiological sources, I've got radiation survey meters, and I've got different shielding materials like concrete, lead, paper, things like that. And we actually figure out what can stop the different sources of radiation. Everything I use is safe. It's actually educational sources, but you can buy a gamma radiation source for educational uses. Then there's beta radiation, a particle having a mass of an electron. So it almost has no weight to it whatsoever. It can be charged with a negative or positive charge, travels a little bit farther, 20 feet. Internal hazard due to its short range, and it also may affect you externally. So in other words, it can get through your skin and penetrate into your body. This we can also stop with some plastic or some lightweight metal, but it can go through our skin. Then we've got the stuff that made the Hulk, right? So we got gamma radiation or X-ray. These things are different types of radiation, but they are very similar in behavior. It just is a difference in how it is produced. And you're probably familiar with an X-ray, right? How many people here have had X-rays? So gamma or X-ray radiation has no charge. It's got no mass to it at all. Because of that, it can travel very, very far, very penetrating type of radiation. So it's going to go right through our body. It's a whole body hazard. So it can affect us externally at great distance. And the way that we prevent this from reaching somewhere where we don't want it to go is from something very dense like lead or some thick concrete. And then finally, we've got neutron radiation, which we don't really have much of in the world of commerce. And it's very difficult to stop. In fact, there's a neutron lab. It's a collection device that's in some incredibly deep lake in Canada. I can't remember where it is, but water helps to slow it down. So they've got this neutron collector at the bottom of this very, very deep lake in Canada to try to study neutrinos or neutron radiation. So the way that we stop this is something that's got a lot of hydrogen in it, like plastic with concrete. So they would actually take something thick like lead or concrete and then put a sheet of plastic in front of it. Now, how do we find this stuff? So radiation does not have a smell, does not have a taste. You're not going to know it's there. So we need to use devices to detect it. This here on the one on the left is an example of a Geiger counter or a radiation survey meter. The thing here in the middle is called a radiological dosimeter. And this here is only going to look at gamma radiation. And inside this is actually a little graph. It's a little scale that you can actually look at yourself and see where that line is. And the line is going to move up the scale the larger dose that this pen has. And you're supposed to wear it on your lapel. But there's supposed to be a health physicist or industrial hygienist that checks this for people who have to wear one of these. And then we can have, some different kinds of shielding and method devices to try to detect it and protect us from it. That's it, folks. That is our physical and chemical properties of hazardous materials. Through my 6 years of practice, it's those things that most often come up as far as a concern on what I need to do to protect a worker with chemicals. Vapor density, vapors, vapor pressure, gases, lower explosive limits, the form that the chemical's in, what kind of PPE do I need? Is a HEPA filter on a ventilation, a negative air machine going to work? Is it not going to work? All those things are really important. And again, you've mentioned a lot of classes that you teach that will touch everything that we mentioned in here. With that said, let's look at the pocket guide here real quick. So this is our pocket guide. This is the newest version. They haven't come out with a new paper version yet. And it's got a lot of information on it. So here I'm using hydrogen fluoride as my example. We've got a chemical formula, HF, so hydrogen and one hydrogen atom and one fluoride atom is what that chemical formula is, but you can see a big thing in here. CAS number, chemical abstract service number. This is a identifier. It's the chemical social security number, it's fingerprint. There's only one CAS number for each chemical that is in existence. This is the reactive toxicity registration number. Here we got your IDLH, a conversion, so you can go from milligrams per cubic meter to ppm. These are the things that are located in the DOT, the UN number, the guide number, so you can cross-reference what you find here into that orange DOT book. Synonyms and trade names, they might call it something different. So example here, I've got anhydrous hydrogen fluoride, right? So they call it by a couple of different things. We've got our NIOSH and OSHA exposure limits, a physical description of whatever chemical it is, measurement method. So if I'm going to collect a air sample or a personal worker sample, I have to make sure for it to be first off legal if I'm looking at worker exposure limit, that I'm doing it in accordance with these collection methods. And I certainly, if I'm ever going to end up in court, don't want to do anything different. So I want to make sure that I can prove I did things along the same standard of care as what's required of me. Bunch of chemical and physical properties. These are things that we went through a lot today. We've got molecular weight, boiling point, solubility, flash point, ionization potential. We didn't cover that one, but this is the amount of energy that you need to ionize a chemical and kick off an electron. And I do talk about this when I discuss air monitoring, because we use ionization potential when we use an photoionization detector or a PID. We have to know a chemical's IP in order to select a PID to use out in the field to detect that vapor or gas. Relative gas density we covered. We looked at specific gravity, vapor pressure. Freezing point, we didn't go into that. No, we did. We did cover a melting point and freezing point. Then we got upper explosive, lower explosive, and then whether or not they designate it as a flammable gas. Personal protection, sanitization, the respirator, the pocket guide also covers respirators. And remember back, NIOSH are the only ones that certifies respirators. And then they give guidance on what you should be using for what chemical and at what exposure level. Incompatibilities and reactives. So we mentioned, reactive chemicals. That could be important. So it gives you some things that you do not want to mix this thing with because it'll cause a reactive event. Then we've got exposure routes and symptoms. Remember back to the toxicology class that we did, how does stuff get into our body? They're going to tell you here in the pocket guide. And then first aid measures. So not for nothing, but that's a lot of information in this book. Now, I agree with all of you. There's no way in hell this is going to fit in a pocket. However, it does have a lot of information. So if you happen to have a satchel or a glove compartment or whatever, right? This is a handy book. Out of my library, and I've got behind those doors back there, if you're ever wondering, no, there's not a monster in the closet. And I don't send the kids there when they don't behave. I have I have a library back there. It's just a wall of books. I don't use anything as much as I use this pocket guide. Doesn't mean I can remember what the hell all these little acronyms and stuff are. I still have to go to the prefix and look them up, but I use this a lot. With that said, if folks, we're going to do an activity. So we got, how many people are on, Nicole?
I don't know, Bernie. Math's not my strong suit. No, we've got all 13 people. So
right.
I've got the breakout rooms all ready to go. I just need to know.
Yeah, so let me get this. Let me get this up here.
Yeah.
Oh, I forgot to share the screen. I'm starting to not like Zoom.
What?
Yeah.
Bernie.
Too much Zoom.
Breaking my heart.
It's killing me. That's not what I wanted to do.
Bernie, that's a nice picture of my classroom.
What's that?
So that's a nice picture of my classroom. The one you just had up.
Oh, I did?
Yes. That's Russell Vittori in that picture.
Oh, okay. I'm trying to find out. Oh, this is your place. Yeah, so Wayne sent me this, I think. This one here? All right, let me find out where the heck I put this thing here. Give me just a second. Yeah, no, they're starting to have research come out with Zoom. One is we're not supposed to be looking at our own image that long. And because we start to pick up on our own cues that we're giving ourselves, if we frown and stuff, there's a reason why we can't walk by a mirror and not stop and look like the canary in the cage, right? And so what's happening is the more people are looking at themselves in Zoom, they're starting to find that they are overreacting to people's facial expressions out in the real world. So if somebody's frowning, they're freaking out in the real world. So although we use this tool to get us by, at some point we got to leave Zoom behind. I'm trying to remember what the heck I called this class. Ah, here we go. Here we go.
How long you think we should have the breakout rooms open for, Bernie?
I think 20 minutes to do the work. So what I'm going to do. All right, now I'm going to try my sharing of the screen. Where'd you go? There you are. Here we go. This will work. All right. We should see this Word document. So this is an actual manual that I typed up for this course. So it goes through a lot of what we said in Word form. And at the end, there's this activity. So I have it listed here for 45 minutes, but we're just going to do it 20 minutes as a breakout room and then debrief it 10 minutes. We've got some questions here that you're going to answer after you look up some information in the pocket guide. So if I could have whoever you designate as group 1, Nicole, please look up information for asbestos and MEK. Whoever is group 2, please look up info for cadmium and toluene. And whoever is in group 3, please look up information for gasoline and sulfuric acid. So you find this info in the pocket guide, and then you're going to answer these questions about those 2 chemicals that you're assigned and what you looked up in the pocket guide. Make sense? And if you were doing this, on your own, especially in person for a class, I would let each group do all the chemicals and even assign some of your own. So, if they work with a certain solvent and stuff like that, go ahead and switch some of these out or add a couple. That's why I've got some empty boxes here. So, work this activity so it'll make sense for your audience. With that said, let's go to it, Nicole.
Okay, that sounds good. And you guys, in your manuals that I sent out right before class, this is at the last couple of pages of that manual if you needed to pull that up and have that ready. But here we go. I'm going to send y'all away. See you shortly. Sweet.
Is this going to be a course that we're going to have to teach separate, or is this kind of a supplemental for our other things that we teach?
Geez, you would have to ask the hard questions. I don't know. I mean, I put stuff together to kind of get us through, the COVID times, and with the understanding that we have a pretty big group of trainers, I try to pick things that might help, maybe give you a little bit more background or foundation in some of the other related stuff like CASCOM. So no, I mean, you don't have to teach this if you wanted to, sure, it's up to you guys. I don't know, Nicole, can you answer that better? I just work here.
No, I think you're right, Justin. I think it's going to be more like a supplement for any of those additional classes that you teach. I think all these things kind of roll up into those. And if you needed to pull certain things regarding the hazardous, properties, we have this course to fall back on. It'll kind of be the same thing when we do some more in January of those types of courses, not necessarily standalone, but more supplemental, and to give everybody those additional resources when you are teaching those hazardous type health and safety classes.
Yeah, because I mean, this stuff will help with OSHA, and it'll also help with the confined space courses that I teach too.
Yep.
Hey, Bernie, and this also plays into the PELs, MUCs, TWAs, and all that stuff, calculating all that stuff. So this plays right into that.
Absolutely. I mean, you can look at something that's got, a PEL, right? And you can look then at the vapor pressure. If it's got a high vapor pressure, you can say, well, boy, I really want to worry about that because it's likely that's going to be up in the air around my worker. And the other thing is I'd like to see us, teach some more HAZWOPER classes. I know that CPWR does it through a grant that they get from NIHS, which I did a lot of work with them as a consultant and also when I worked at UMass Lowell and their grant awardee. But I mean, we're more than qualified to do our trainers that I've seen to do our own HAZWOPER classes, and then like, I don't know, it's just stuff I'm thinking of. How can we branch out and have more to offer, as a training organization, the health and safety realm. So if that's something of interest, we can certainly go down that route. And this would be a module, in a 40-hour HAZWOPER class, something like that. Good questions. Yeah. And if you guys come up with anything or girls come up with anything that you want to do, one of my goals over the next year is to reach out. I'm trying to figure out the best vehicle to do this, to do a hazard assessment. And I've done that on my own through literature and through talking to, a couple of our ATRs and stuff like that, and try to categorize all the hazards that any IUPAT member might touch, whether it be wall covering, floor covering, painter. And then from there, I came up with, are there any regulations that govern that hazard? Or if there's not, is there a standard of care, like from NFPA or something like that, like a consensus standard? Then from there, do we have to have a written program to meet the requirements? Yes or no? And then do we have to have a training program? So one of my goals is to go, and again, I got to find the most efficient way to do this. Basically just solicit, what you feel like all the hazards are. And then I'll match those up to the one that I did. And the one I did, it's like, I don't know, 12 pages, it's big. And then, from there, then I can start to develop programs that affiliates can use as a model program if you need one, both on a construction site or at a training center. But if there's something, until that happens that you find that you'd like to have as a class for health and safety, let me know, because, I can get it done and we can do something with it. So, and I've been really excited, to see all these, all the training, all of you that have been coming on and doing these classes and that I've met, because I think that we've got a really high caliber group of trainers, which again, I love, because you've heard me broken record this, but there's no better bang for the buck than to do health and safety training, especially at the awareness level, because it just does so much for a worker. But yeah, so thanks for asking that question. And again, my email is always open to you. If you've got an idea or something, I don't know what the channel is we have to do this, if you have to run it through your training director or whatever, or however you want to do it, let me know and I'll see what we can come up with.
Hey, Bernie,
Yeah.
just speaking on email, I sent you an SDS of a dry fall product. So if you want to look it over so you get a little more familiar with it.
Sure, absolutely. Thank you.
Yeah.
All right, so with that said, we don't have to go through everything that you found here, but I'm just going to ask this open question. Did anybody have any difficulty or concern finding this information for your chemicals? Were you able to find the CAS number, the form that it's in, vapor pressure, all that stuff? Okay, good. Oh, great. I look out the window, I see the wind's whipping up. I love that when I snow blow and it's windy out too, and I get it right in the face. That's going to be fun. All right. Any of the chemicals that present a fire or explosion hazard? So the ones that you looked up, did any of them present a fire or explosion hazard? We had asbestos, MEK, cadmium, toluene, and
Toluene.
yep, definitely. Did somebody have gasoline?
Yeah, we had gasoline. It's yeah, you had a problem with that.
All right, how about let's see. How about MEK? Did that have a vapor pressure and LEL and flashpoint?
We found them pretty easily.
Yeah. Okay. So would you consider MEK to be a fire hazard?
Yes, we're painter. We kind of have to make sure to take care of that.
Okay, good. Is a chemical likely to form a high vapor concentration? So for there, we look at vapor pressure, right? And what would you say? Any of those chemicals you looked up form vapors?
For MEK was 78 mmHg.
That's high. How about toluene?
Yes.
We got 21.
Yep, that's high. How about gasoline?
Yes.
Yep. And how about sulfuric acid?
We said no.
Good. Yeah, so sulfuric acid, it's got a low vapor pressure. It's like 0.00 something. Is that right?
0.001.
Oh, okay, look at that. So yeah, so that's a low vapor pressure. However, depending upon how you might use that, if you're adding heat to it, you can vaporize that enough where if you're standing near it, you'll be able to smell it. And of course, that's not good. But as it is by itself, it's not too much of a concern for a vapor issue. Are the vapors or gas lighter or heavier than air? How about for MEK?
Heavier.
Heavier. And what page is
Heavier.
MEK on? Was it? Okay.
Hey, Bernie, the page
It's
number is gonna change with the year,
72.1.
with the addition.
What's that?
The page number is not the same on all the volumes, depends on the year they have it.
Yeah, I got the silver one. This one.
That's what, 07, I think, isn't it?
Yeah, let's see.
MEK.
Basically, if the molecular weight of the chemical
Page
is
36.
29 or higher, it's gonna be heavy, right?
I think it was 72.1.
Okay, yeah, so that's gonna sink because that 29 is air. How about toluene?
What do you need? The molecular weight was 92.1.
Yep. All right. So 29 goes into 92.1 more than 3 times, so that would sink. How about good old gasoline?
Heavier.
Heavier. Okay.
Vapor density of 3.78.
Okay, great. All right. Do you have any other concerns about any of the chemicals that you looked up?
I have a quick question, Bernie. Sometimes you see it listed on the SDSs or different documents, LFL, LEL, what's the difference?
Lower flammable limit or lower explosive limit, it's the same thing. They should just use LEL and UEL. They shouldn't use the FEL. It just gets confusing. Standardization is important. Good question.
Yes, for MEK.
Let's see. And so, I'd be concerned about some of these that are more toxic, right? I know asbestos is a carcinogen, cadmium is a carcinogen. I'm nervous about gasoline because it's just so flammable. And then I'd be, concerned about sulfuric acid because it's a strong acid. But that's generally, the kind of a rule of thumb of how you do a chemical assessment. You find out what you're working with. You look up, the basic physical properties. Then you go and you look up what the toxicological properties are. And then you can determine how risky it is for a worker to work around that stuff. And then from there you can, determine if you've got to control it and to what extent. And that's how it goes. And you might not be able to just stop with this book or an SDS. You might need to use other resources. And there's a lot of good stuff out there, to use. There's the condensed chemical desk reference. There's Corrosivity and Duels, toxicology, basic science of poisons and other stuff. But if you happen to do any of this and you got questions, give me a buzz. Again, the general contractor or whoever the employer is responsible for doing this stuff. I want to make that very clear, but it's not a bad idea for labor to be doing some of its own work, right? To make sure that what is being done should be done. So with that's it. That's the end of our course. Anybody have any comments or questions?
Hey, Bernie, if I can make a recommendation, when you do activities like this for future reference, can we link it more to the PEL, TWA, how the number you're looking at it? Because our guys don't necessarily work 8 hours. The industrial painter could work a 16-hour workday, 15-hour workday. That's going to affect your PEL and TWAs, so that our guys know that.
Yeah, so we when we did the toxicology class, we looked at PELs and stuff like that. But for this, we just wanted to focus on you know, properties, chemical and physical properties of hazardous materials, which don't include PELs or toxic, you know, toxic related phenomena. That was in the toxicology class. But if I am doing work that has to deal with, you know, a PEL or a TLV, something like that, yes, I can do that. And in fact, you know, there's a calculation that you do, you know, to be able to adjust what the concentration is from an 8-hour or a 10-hour exposure limit up to the time that you're actually working. So yeah, I can do that for classes going forward. And in fact, I think, Nicole, are we doing the toxicology class again during the winter?
Yeah, we sure are.
All right, so there we go. So I'll throw that in there. Good comment. Yep, we can do that. You mean nobody works an 8-hour day anymore? It's crazy in this country, right? Man. Crazy. All right. Anything else? All right, folks. Well, thank you.
Thanks, Bernie.
Yeah, thank you very much. And if any other comments or questions come up, you know, throw
Thanks,
them
Bernie.
in the email. Thanks, everybody. Hey, Merry Christmas, Happy Holidays, all that good stuff.
Same
If
to you and
don't ever
yours.
see me again,
Thanks,
it's
Bernie.
because the snow got the best of me.
Merry Christmas,
Thanks,
everyone.
Bernie.
Bye.